All right, welcome back to the probability slides. Let us scoot on down to where we were. A very fun problem with cars and goats last time. And now we're here to try and remember some of our conditional probability skills. Are you ready? Okay, so here's a set of characters, A through G. Okay, let's pretend that we permute them. We put them into a random order, and every permutation is equally likely. So all the way from like A, then I can pick D, and then C and B, and then, I don't know, G, F, and E. That's one permutation. You have all of those, right? How many? 1, 2, 3, 4, 5, 6, 7 factorial of them, right? A lot. So here are some events that could happen when you permute these letters randomly. Maybe the letter B falls in the middle with 3 before and 3 after, and that was pure luck, me doing that. So it would end up like that. And okay, that's event A. Then event B is the letter C appears to the right of B, but it doesn't have to be immediately to the right. So here is C and B, as long as C is somewhere to the right. It doesn't matter where it is. It could be right next to it, it could be farther away, as long as B comes before C. Okay, that's the next event. And then the last event, call it C, is that the letters D, E, F occur in that order together. And so they have to be like this, but they could be anywhere in this permutation, be at the beginning, at the end, in the middle, and then all the rest of the characters are around them, okay, on either side. So that is the setup. These are the 3 events. And so I'm definitely going to have to make a new slide for this, but let's first calculate the probability of each individual event, okay? So go ahead and give that a try, and then we'll come back and do it together. So it's time for me to make a new slide, that's for sure. I think I can do it with that one, yeah. And let's make it blank. So for A, we want to calculate the probability of events A, B, and C separately. I'll do it up here. So the probability of event A happening, what is that? So the letter B falls right in the middle. So it's as if we have chosen the spot for B ahead of time, and then the rest of these can be shuffled around however we want. So B has to go in the middle. We pick that number for it. So there's only one way to do that. And then how many ways are there to shuffle the rest? 6 factorial. Now there's only 6 characters to shuffle. See that? So P of A is 6 factorial over how many ways we could shuffle every character, which is 7 factorial. Okay, so that's P of A. P of B now is what? Now for this one, we have the letter C appearing to the right of B, but it doesn't have to be immediately to the right of B. Okay, so that's okay. The trick here is to notice that no matter what permutation you end up doing, either this is going to happen, B comes before C, or this is going to happen, C comes after B, or C comes before B. So these are your 2 options. No matter what permutation you pick, these are your 2 options. And the idea is to notice that all that they differ by is the location of C and B. You could swap them and put them right back, and you have just as many permutations. So there's an equal amount with B on the left of C, and there's an equal amount with C on the left of B. That's the trick, okay? So it's actually 50%. 50% of the time does this ever happen. Okay? That's a tricky one. This is a tricky one. So do pat yourself on the back if you're getting any of this. This is 0.5. It's 1/2. P of C now. The letters D, E, F occur together in that order, which we've done a problem kind of like this. These are stuck together now. They are 1 character. So now I have 1, 2, 3, 4, 5 characters total to permute. We just treat D, E, and F, because they got to appear in that order, as just 1 character. And so it's 5 factorial. You see that? 5 factorial ways to permute that different kind of string, okay, over 7 factorial. So these are our permutations. All right, and that's A. Okay, that wasn't too bad. So now we're on to calculating the conditional probabilities. So what is the probability of A given C? What's the probability of A happening knowing that C has happened? So that's going to be the probability of A and not B, A and C both happening over the probability of C. Okay, so we know that one. We just need to figure out this, and then we can make an actual answer. So when does A and C happen at the same time? How can we figure that out? Okay, where do they overlap? When you have D, E, and F occurring together, and then B falling in the middle. Okay, how can we do that? So when we have both of these events occurring, our strings look like this. We have B in the middle, and then D, E, F has to appear together. So because B needs to be in the middle, D, E, F better be either over here or over here. Okay, it's got to be on one side of the B. Okay, so let's pretend it's on the left, and then we get to permute the remaining 3 characters in any way we want. So that's 3 factorial ways to do that. And then if the B's right here, and we choose to put the DEF over here, we again have 3 factorial ways to permute the remaining characters. Everybody else is fixed. So the answer for PA intersect C is the, well, it's going to be, how many ways can we do this? 3 factorial over 3 factorial. And that's going to be that over 7 factorial, right? That is total. Okay, so that's P of A and C together, intersect them, and the rest is history. Oops, I didn't move the F. And then we still have P of C, which we already know, right? So that's the answer there, and so that's that one. Okay, so let's try some more. And I think just to save time, let's skip C and have these ones. Okay, this is the new C. What's the probability of A given B? Okay, and then we'll figure out which ones are independent based on what we know. Okay, so let's do A given B, and so that means we're going to do this one. We need to know the probability of A intersect B over the probability of B. So B, probability of B, again, we know. We need to figure out how often do the events A and B happen together. All right? So let's do it. So B is in the middle, and then C appears to the right of B. Okay? That is the idea. So with B in the middle, how many ways are there to do this? We have to put C over here in one of these slots, okay? C's got to go in one of these because it's got to be to the right. So how many ways are there to do that? There are 3 ways to put a C in one of these spots, yeah? So let's pretend without loss of generality that we picked this one. And then, how many more characters still need to be permuted? It's 1, 2, 3, 4, 5, okay? So once we made our choice for C, there's 3 ways to do it. Then we have to permute 5 more characters. So this is the total number of ways to do both, with B in the middle and C to the right of B. Okay? That's A and B together. And the probability of this is just all that over 7 factorial again. Yeah? That's the idea. 3 times 5 factorial over 7 factorial, all over the P of B, which we've found out previously. Okay. So that's our probabilities, and now let's figure out which of these are independent. I think we can only figure out if A and C and A and B are independent. So let's change this question around since I deleted one. Are they independent? So the question is this equal to the probability of A? If it is, we know that it's independent. You see that? That was one of the requirements for being independent. So is this equal to the probability of A, and is this equal to the probability of A? If they are, then we have found actual independent events. Okay? So this is the probability of A. Let's see if this is equal to it. Let's see if this is equal to it. And I don't want to force you to do all this math. Let me go look up the answer, and that will be that. So it looks like this one, A and C, are not, and A and B are independent. Okay? So it just so happens, if you do the math, apparently P of A given C is not equal to P of A, but P of A given B is equal to P of B, and so this one is not independent. A and B are not independent, and or sorry, A and C are not, but A and B are. Okay, so that is the idea. That is A through D. How is that? So now we are very good at our conditional probabilities and discovering whether or not things are independent. And that brings us to another way of manipulating conditional probabilities. So sometimes, like, we have P of B given A, probability of B happening given that we know that A happened, but really we deep down want probability of A given B. We want to flip it. And it's possible to flip it. Let me show you. So this is the formula for using this one, and this one to get the other way conditionally. And let me prove this to you. It's really not a hard proof, because this is how, like, the conditional probability gets made, right? P of E given F is equal to P of E intersect F over F, right? So let me show you this. What we want, where have we gone? So remember this, P of, I guess, A and B is equal to, let's do P of B given A is equal to the probability of A and B over the probability of A. And so in order to solve for the probability of A and B, we can just bring this over to that side. So that gives us P of A times P of A and B, or sorry, P of B given A equals P of A and B, A intersect B. And we can use this in this formula. So what does P of A given B have to be? It needs to be P of A and B over P of B. We have this one. We assume that we did. And then this one can be achieved through this. You see that? We just plug it in. You just plug it in for that right there. And that's how you solve for it the other way. Isn't that cute? That's quite nice. And actually, you can get away if you don't even know P of B, if you don't know the probability of B happening by itself. If you instead know the probability of B happening given that A didn't happen, okay? It's kind of like the opposite of P of B given A, okay? Because in that case, the probability of B happening is this one plus that one, okay? And it's very easy to get probability of A not happening. You just do 1 minus the probability of A, right? So that's easy to find. That one's easy to find. We assume that we know this one, and then we're given this and we're given this, all right? So why does this make sense? Why does P of B become that? How does that mean anything at all? So the trick is to notice that this times this, if you follow this equation, depending on which side these are on, doesn't really matter, you're going to get, this becomes P of A intersect B. Do you see that? And this one over here becomes P of A bar intersect B. You see that? So this is definitely going to be equal to P of B because, like, here is the probability of A and B happening. Here's A, here is B, A, B. Here's the probability of their intersection. And here's the probability of the intersection of not A and B. So not A is everything outside of A. So it's, when it's part of B, it's everything over here. And you just add those two and you get all of B. Do you see that? That's the beauty of it. So this also works if you don't even know the probability of B. And this is Bayes' theorem. It was invented by someone with the last name of Bayes. And it's a nice way to flip-flop your conditionals. It's beautiful. Okay, and the classic example of why you would ever want to do this is usually has to do with like illnesses and like tests for illnesses or something, some kind of test. Okay, so let's suppose that we have a really nice test for something like maybe the coronavirus, and it's 90% accurate when someone has the illness. Okay, so what I just said in this sentence is that the probability of, this should really be lowercase, but some people like to use capital P's. I'll just keep it. The probability of the test being positive given that you have the illness. So when someone has the illness, okay, and the test gives a positive reading when someone has the illness, 90% of the time. That's accuracy. Okay, and then the illness is a rare one, okay? So it's not like the coronavirus. It only happens in 5% of the population. So we say that the ground truth, the probability that somebody ever has the illness at all, is 5%. And so that means that you're not sick, you don't have the illness. The probability of that actually happening is 95%. See where I'm going with this? And so now, okay, that means that we can think about figuring out this, okay? Like we had this one, but so we know how accurate it is when someone has the illness, the test, but what does it mean? Like how often does somebody who tests positive actually have that illness? See? So probability of has illness given that your test was positive. That is where we use Bayes' rule, okay? And so we need the other sides of things. So what we're going to do is we're going to follow this rule with this fancy thing as well, okay? So we're going to do probability of the opposite. Probability, this is equal to the probability of positive given you have the illness, and that is times the probability of A, the thing on the left, probability that it's positive, over, are you ready? Then we're going to do the probability that, because we need to calculate these intersections, the probability of, technically it's all this stuff up top again. It's probability of P, it's positive given you have the illness, times probability of P, and then plus the probability of it's positive given you don't have the illness, right? Probability given that bar. Given not has illness, but no illness, okay? And then that's times the probability of having no illness. Okay, so that's the answer, and we just need to fill these in. The probability of it being negative and not having the illness is apparently 0.8. So we say that somebody did this research, like the test is 80% accurate when someone doesn't have the illness. So that means it's going to tell you that they don't have it. It's negative 0.8% of the time, which means that it messes up. It tells you it's positive when you don't have the illness 20% of the time. Okay? That's the idea. And so now we have everything to fill in. Okay? So we can plop all this in here, and it's apparently going to be 0.9 times 0.05 over 0.9 times 0.05 plus what's positive given no illness, 0.2 times what's the probability that you don't have the illness, it's 1 minus the probability that you do, 0.95. Okay? And let's go quickly and figure this out. I'll open up my calculator and I'll be right back. And so I was lazy this time and I just used Python because it was easier. And so it's about 20%, 19%. This is the thing. 19-ish%. Okay, so the probability that you that you have the illness given that your test came back positive is very small, actually. And it has to do with the fact that it's a very uncommon illness. Okay, so that kind of throws off your intuition, and this is a great example of the Bayes rule. Okay, make sure I'm actually recording, yes. And so that is the end of conditional probability for us. Let's move on to something involving some more numbers. And this one's going to be interesting. So random variables is the new topic. So a random variable, and we can give it any name we want, x is fine, it's a function, actually. It's a function from the sample space, so it takes like an event, and it gives you back a number. So from the sample space to the real numbers, and the number that you can get back is whatever you want it to be. Okay, so you can also like misuse notation and say try to call the function on the whole sample space, and apparently this is called the range of the function. This gives you back the range of the function. That's what it means. Okay, so here's an example from your book. We have two dice, okay, a blue one and a red one, and so we can make a random variable, call it D, to represent what happens when you roll the dice. Okay, that's the idea. And so you give it an outcome, it gives you a number. All right, so the number that each outcome represents is going to be the sum of the numbers on the dice. Okay, you see that? That is going to be the idea, which means that our random variable's range is this. D's range, you give it an event and it sums the dice from that event. Okay, that's the idea. So these are all the different sums you can have of your dice, from like 2 snake eyes to 2 sixes. And so that's what the random variable will give you back. You give it like 2 dice, the outcome, some little s, and then it gives you back the a number based on that outcome. So like maybe you rolled a 5 and a 4, and so you get back the outcome of, or you just get back the value of 9. Okay, and so you can have a random variable give you back any number. Okay, that's the idea, as long as it's a real number. It goes from the sample space to the real numbers. That's all it is. So that's not too bad. So this is a random variable where the number you get back from D is 9. This is where you get back D being 5. Okay? Here's another example from the book. So let's have another random variable, M, and it's going to be, it's going to represent the sum of the red and blue spinners on the right. So you spin these 2 spinners, the blue one and the red one, randomly. They randomly land on numbers, and you have an outcome. Okay? And when you give it, like maybe your outcome was 3, 2, and it's going to give you back the sum. Okay, so this sum here is 5, and so that would be the output of this function, this random variable. That's the idea. Okay, so now we can talk about distributions over each random variable. So, and this is where things get fun, because we can start figuring out like, okay, which of these is more likely, and like with what probability? What's the average number that we get back from our random variable? Okay. So the distribution of a random variable, it is just going to be another set, this time it's of pairs, even if there weren't pairs to begin with, of all the things from the range of the random variable, and then the probability that the random variable was equal to that value in the range. Okay? That is the idea. So it's the probability of each random variable occurring. That's what the distribution will tell you. So for example, here is a possible value of the random variable. This is M still, I think, and it could be 2, because those 2 spinners could both land on 1. Yeah, that's fine. And how often does that happen? That only happens 1 out of 9 times. You see that? That's the probability that it happens, because there's only one way to get there, right? The event that the random variable M equals R equals 2, so that's, this is M equals 2 case. That only happens when the 2 spinners landed on 1. There's only one way to do that. Okay, so that's the event. And so that's the idea. We can make this table. Like when R is 3, like it could have been 1 and 2, or it could have been 2 and 1. Yeah, so there's 2 ways to do that. And this is if M is equal to 3. There's 2 ways to do that, which means there's 2 out of 9. The probability of that happening is 2 out of 9 times. Yeah, and then same for 4, 5, and 6. Apparently it's very easy to make 4, because there's a lot of ways to do it. 1, 3, 2, 2, and 3, 1. That those sum to 4. This is M equals 4 for the random variable, and yeah, it happens 1/3 of the time, because you have 3 over 9 possibilities total. Yeah, that's not too bad, I hope. This number, though, the fact that we get back a number means we can do cool things with it. We can say, how often should it appear? What do we expect to get back from a random variable, right? Because we don't know what it is. It's like a random process that's producing the value of this variable. like this m value. It could be 2, 3, or 4, but the probabilities are different for the 4, the 3, and the 2. You see that? We can talk about what's the expected value that we should get back, like if we average it together over time. Like what's the expected average value we should get back from our random variable? And the way that we denote that is we say e bracket x. Okay, so if the random variable is called x, we say what's the expected value of that random variable by putting it around an e and some brackets. Okay, and the expected value is actually going to make a lot of sense, I promise, and it's going to be a weighted average. Okay, so that's my hint. There are two ways to calculate it. One is you go over all the different outcomes in the sample space, and you figure out, okay, what's the number you get back from the random variable when you apply that function, and then you multiply it by the probability of that ever occurring. Okay, so it's like a weighted average. So like if the probability was like 0.05, and the number that you got back for this particular outcome in the sample space is like 12, you'd multiply these together, and you're going to make a sum of all those. And it gives you the weighted average, the number that you can expect to see over time in the average. Okay. Alternatively, these actually are equal. The expected value could also be arranged like this. Instead of talking about the outcomes, talk about the values that the random variable could take on. Okay, that's the idea. And then you can just take that value, because that's essentially x of s, right? And then you can also then use the probability that this value was obtained by the random variable. Okay, so either way would work. So this is like, the first way is like saying, okay, this is one outcome. This is 1, 2, that's an outcome. The random variable gives us back the sum, that's 3, and so we're going to multiply 3 by how often do we get back 1, 2, right? And that's 1/9 of the time. 2, 1 is the same. 2, 1, the random variable x of s for this event gives us 3, and then how often do we get back this exact outcome? Well, it's 1/9 of the time. Okay, 3 times 1/9. This way of doing it is like, okay, let's just consider how many ways we could make 3 get back received from our random variable. And there's 2 different ways. You see that? It's a bit faster that way. So it's like, okay, yeah, I could have received 3 times, okay, what's the probability that I actually got here? 2/9. So instead of adding these and these, we just go straight to here. That's the same number. Okay, that's the idea. So it's easier to work with this one. It's a bit faster usually. And so really it's just a weighted average. The expected value of this m for these spinners, of the random variable n, which is the sum of the 2 blue and red spinners, is just 2 times 1/9 plus 3 times 2/9 plus 4 times 1/3 plus 5 times 2/9 plus 6 times 1/9. You just add them and multiply. It's a weighted average. And so it ends up being 4. That's the expected value if you spin these spinners enough and you just take the average of what you get back. This is what you can expect to see. 4. That's the number that it's supposed to give you back, this random variable. That's the sum that you should expect to see. Okay? And I hope that that's a bit intuitive. I'm trying to make it a bit intuitive. This is one of those examples of probability where it's not too bad, unlike Bayes' rule, unlike these illness things. You can also do conditional expectations. Okay? Those are essentially the same. It's just you only consider pieces of this entire sample space. So you can figure out, okay, what's the expected value of this random variable m when blue happens to be 1? And so what you do is you figure out, okay, where are all the times where blue is 1? This one, and this one. And then you do your random variable game. So, okay, we could get 2 back because we could have used this one. Random variable could be 2. And how often do we get this back when these are our 3 options? You see that? If those are our 3 options, it's only 1/3 of the time. You see that? That's the key. So now we only have 3 options. It's this one, and this one. So 2 times 1/3. For the 2, it could land on the 2 1/3 of the time. And then 1/3 of the time it lands on the 3, because you have 3 options only now. 3 times 1/3 plus 4 times 1/3. Okay? That's the idea. And so the expected value of this random variable, when you know that the blue spinner landed on the 1, is going to be a smaller number. 2 times a third plus 3 times a third plus 4 times a third. I guess I can take a third out of that. So it's a third times 2 plus 3 plus 4, which is 3. So expected value, which makes sense, it's the 3. You spin these spinners enough times, you know that the blue is always a 1. Well, the expected sum that you get back is 3. If you spin it enough, take the average. That's the idea. Okay? So hopefully that makes some sense. That is the expectation of a random variable. Okay. Moving on down. Now it's your turn. Okay, so here is an experiment. We have a red die and a blue die. We're going to throw them. So they're going to randomly land on numbers, of course. And let's let a random variable x be the product of those numbers that we see. Okay, so like if our outcome was, I don't know, 2 and 3, the random variable would be 6. Okay, so first figure out the range of x, and then figure out the distribution of the random variable x, and then finally figure out the expectation of that random variable x. Okay, so give that all a try, and then we'll do it together. Okay, I've written a nice little program to do all of this for us. So it's going to roll 2 die, figure out their product, and then keep track of how many outcomes there were. There'll be 36 total, but why not keep track of that? And then, yeah, every time you see this product again, the same one, you're going to add it to a hash table. Okay, it takes an outcome, gives you back the count of how often it appeared, and so yeah, at the end of this you'll end up with a hash table that you can iterate through and just print out each outcome and how often they appeared, while adding to our expected value, because it's always multiply the outcome, that number that we get back from the random variable, divided by the probability that it occurs, which is the number of times we saw it over the total outcomes. Okay, and so that'll build up the expected value for us, and so we can run this. Here are all the different ways to do things. You can get a only one way, because you're rolling die, right? Red die and blue die, so you have to get a 1 on the red and you have to get a 1 on the blue to get a 1. Same for 36. You multiply the 2 6s, there's only one way to do that too. Okay, that is the idea. Okay, so yeah, there's 2 ways to get a 2, because you can get a 2 and a 1, or a 1 and a 2. And so these all count like this, and apparently it's quite easy to get a 6 and a 12 in many different ways. Yeah, and so these are your outcomes. If I just take a screenshot of all of this, this is essentially the answer here. Okay, so here we go. How about we do this? Sure. And so here is, all these numbers here are going to be the range. All these numbers together as a total are the distribution. And then there's the expected value. Okay, that's the idea. And programming helps us to do these things. Okay, so that's the expected value, and it's a nice little number that gives you, like, okay, this is what should be given back to you, right? If you flip a coin and 0 is tails and 1 is heads, the expected value you get back is 0.5, you know? It's a nice weighted average. It makes sense. And you can actually do cool things with it if you have 2 random variables, or just more than one. You can use linearity of expectations to figure out, okay, what's the expected value of, okay, having this random variable give me back its random value, and having this random variable give me back its random value. What's the sum that what's the expected value of that sum? It happens to be the expected value of x plus the expected value of y. That's quite nice. It's a linear thing to do. Okay, this is called a linear operation when this happens. Same for when you multiply it by a constant c. Like this variable is going to give me back a random value. If I multiply it by a constant c that I pick ahead of time, like 2, it just so happens like the expected value of the random variable times that constant is just the original expected value times that constant out on the side. That's crazy, but it's quite useful. Okay, and it does follow from all these definitions. Okay, so the expected value of x plus y, let me prove to you that that is equal to the expected value of x plus the expected value of y. Well, just unravel the definitions for all of this, okay? So the expected value of this big long thing is going to be the sum over all the outcomes of the probability of that outcome times, well, what you get from the random variable, what it gives back to you on that outcome. So it's going to be whatever it gives x the random variable gives you back for that s in your sample space, and then whatever y gives you back, and you add them together. Okay, so that's just following the definition of what is the expected value of something. And because of this, we can distribute the p's. And so we end up with this. It's just the same thing. This is one big parenthesized statement, still the same sum. But then, look what you can do. You can kind of split them off. You can do this sum, this sum. It's the same thing, you just add them in a different way, in a different order. And these two are the definitions of the expected value of x and the expected value of y. And same for this one. Same for this one, you do probability of that event times c times the random variable's value that it gives back to you, and you can just bring this constant outside of the summation because it stays the same. Okay, so that's why those are true, and let me show you an example where they're useful. All right, so let me show you essentially the birthday paradox again. So let's assume that the probability that a person is born on a given date is 1 out of 365. That's what we did for the birthday problem secretly. Don't worry about February 29th. So let's pretend we have a group of 100. What is the expected number of pairs of people who have the same birthday? Okay, we can use expected values actually for this. So the trick here is we can make a random variable that represents like the number of pairs of people who have the same birthday. So let me try and make that happen. So let's make one random variable for every pair of people, and it'll be 0 if they have the same birthday, and a 1 if they have the same birthday, and a 0 if they don't. All right, so let's do this. How many pairs of people are there? Because that's essentially what we want to count. We got 100 people. How many pairs of people are there in that group of 100? There are 100. Choose 2 pairs of people. And so let's make a random variable. Let's make that many. 100 choose 2. That's 100 times 99 over 2. So whatever 50 times 99 is. Let's do that quickly. 4950. There are 4950 pairs of people. 4,950. So let's make P1, P2, ... all the way to P4950. That many random variables. And to be a random variable, you just have to have a number as your output. That the random variables, each of these, let's have them be 0 if the, if the pair represented, like this is the first pair of people, the second pair of people, just order them randomly. If the pair does not share a birthday, and 1 if they do. So do you see that if you summed all these together, that would give you the number of pairs of people who have the same birthday. Okay, and these are random variables. So we now can talk about their expectation. We can make one big random variable, or we can just say the expected value of P1 plus P2 plus ... plus P4950 is the number we're looking for. Okay? This will tell us the expected number of pairs of people who have the same birthday, because we've made random variables for each pair of people, and we'll make it be 0 if they don't share a birthday, and 1 if they do. So the number of 1s that we see here, what's the expected number of 1s that we see here? That will be the number of pairs of people with the same birthday. I hope that that is able to be followed. Okay, that is the key here. And once you've done that, you just need to figure out, okay, we can use linearity of expectations for this. It's just the expected value of P1 plus expected value of P2, that all these pairs of people have the same birthday, that an individual pair of people have the same birthday, 49 and 50. So now all we have to do is figure out, okay, what's the expected value that somebody, a given pair of people, has the same birthday. Okay, so that's what we need to figure out. And it's going to be a weighted average again. So like the expected value that pair I shares a birthday, it's going to be, well, the random variable could give us back a 0. And we need to figure out what's the probability that two people don't share a birthday. And plus a 1 times the probability that people do share a birthday. Okay, so what's the probability that two people are born on different days? Yeah, it's 364 out of 365, right? It's the only, if they share a day, there's that one other day left over, okay? And that's the probability that they do share a birthday, 1 over 365, okay? So really the value of this expected variable is just this. That's what it becomes, okay? So each pair is just 1 over 365. That's the idea. And all of them are equal to that, 1 over 365. So I have 4950 times 1 over 365, and this comes out to a nice number. That's about 13.6. So you can expect to see 13.6 people, apparently, to have the same birthday, okay? Out of a group of 100. That's the idea, okay? And so this is a nice looking number. It's the number of pairs of people and the probability that any one of them is born on the same day as another person in their pair. Isn't that beautiful? So that is the linearity of expectations. It allows us to solve this kind of problem very easily. Okay, now on to like the second to last topic for these slides. We're very close to being done. All right, so let's talk about another way that probabilities can be distributed. And this is all about success and failure. Okay, it's invented by this man with the last name Bernoulli back in the day, and so we have the binomial distribution thanks to him. So let's get some terminology though. We have Bernoulli trials. We call Bernoulli trials any experiment that has exactly two outcomes, success and failure. So like flipping a coin is the standard example. You can just say like, I like heads, heads is success, tails is failure, okay? And the distribution over a random variable defined by the number of successes, it's just a number, right? The number of successes in a sequence of independent Bernoulli trials, I know that's a mouthful, that's what is defined to be the binomial distribution, okay? That's all it means. We're just trying to count the expected number of successes that we see out of a bunch of Bernoulli trials that can end up in success or failure, okay? And each of these have probabilities. There's a probability of success and there's a probability of failure. And it's quite, or it's not easy, but it's not too bad once you've seen the formula to understand why it makes sense, okay? So the probability that you have exactly k successes in a sequence of n independent Bernoulli trials, they can't affect each other. That ruins everything, right? Exactly having k successes out of n tries, so like k heads out of n flips, where the probability of success is p, which means the probability of failure is 1 minus p. We also call that q. It's this. Well, how many ways are there to choose exactly k out of your n? That is a nice thing that we can use, and that's kind of where the binomial comes into play. There's n choose k ways to make a combination of k things out of a set of n things. That's how many different ways we could choose those k successes, whatever order they come in. And then we had this many successes and this many failures, and so we have to multiply by their probabilities. So we picked exactly k successes, and they must have occurred with this probability, and then we had n minus k failures because of that, okay? And that's that probability too. So the probability in total of exactly k successes is this, okay? This is all the ways that it could happen. That's the probability. So for example, let's figure out the probability of rolling exactly 2 heads after tossing 4 coins. So just following the formula, we have 4 coins. We want 2 heads out of that. That's our success rate. And so our probability of success is 0.5. And we had 2 of those. And then our probability of failure is also 0.5. That's Q. And how many failures did we have if we rolled 4 coins? Well, it's just 4 minus 2. It's still 2. Okay, so that is the idea. So let's figure this out. It's going to be equal to 4 times 3 over 2 factorial, which is just 2, times 0.5 to the 4th power, it seems. So let's figure this out. So that is 6 times 0.5 to the 4, and that's 0.375. So that is the probability of rolling exactly 2 heads, which is what you would expect to flip, right? I don't know why I said rolling. I think it's supposed to be flipping, right, when it's coins. It's 0.375. It's not 0.5, even though you might think it should be. It's just 0.375. It's the binomial distribution looks a lot like the normal-ish distribution. That's the idea. Okay, so that is the 0.375. It's technically in the middle, but you also have things on the sides. That's all. Okay, and this is kind of hard work, but the expected number of successes is super easy now that we know all about random variables. Okay, the expected number of successes, so expected number of heads, for example, in n trials is very easy to calculate. It's okay. The number of successes for each individual trial, expected number, is what? Okay, so it's probability of success times 1, because that's what we want the random variable to output if we got a success, and we output 0 if we got failure. So it's that times 0. So this is just p, right? The expected number of successes for a given trial with a given probability, p, is just p itself. So like if you if you flip 1 coin, the expected value of flipping coin I, maybe CI or something, that is exactly 0.5. You can expect it to land on heads 0.5% of the time. 0.5 heads is what you expect to see if you roll 1 coin. That's the idea. And so if you have n trials, this is a constant, and we know what we can do there. That's just expected value of c times this original random variable x. Oh man, that's just c times e of x, which for Bernoulli trials is just p. That's c times p. So if we want to roll 3 coins, what's the expected number of heads we should see if we define heads as success? Well, it's just 0.5 times 3. We expect to see 1.5 heads. Isn't that cool? That's quite nice. That's the expectation. That is the idea. So that is, that's the binomial distribution. That is all about success and failure. Okay, now we're experts at that. So let me show you a nice example, and then I'll have you go off and do it. So let's pretend that, I don't know, you meet a gambler somewhere on the road, and the gambler tells you, I have 2 coins. One is fair. One is a cheating coin, biased. All right? We don't know which one he's about to choose, but he tells you, like, okay, this one's fair. It has a 0.5 chance of landing on heads. This one, this biased coin, has a 0.3 chance of landing on heads. He's going to take one of these out of his pocket, and he's going to flip it a few times for you, and it's your job to guess which one he picked out. Was he tossing the fair coin, or was he tossing the biased coin? So without knowing which one he was, which one he picked and was using, you tell him, okay, flip the coin 10 times and I'll make my guess. So you're going to say, all right, this is my plan. If the number of heads is at least 4, I'm going to conclude that the coin is fair. If it's less than 4, you're going to say that it's biased. And so what I want you to do now is figure out what's the probability that you were wrong if the coin was fair, and what's the probability that you were wrong if the coin was biased. Okay, I will admit there's a lot going on in these questions. Let's do A first. We reached an incorrect conclusion and the coin was fair. So we thought it was biased, okay? But it was really fair. So that means we saw less than or equal to 3 heads. And it was a fair coin. So what is the probability that that ever happens, all right? So we can just do this instead. We can say, what's the probability that we saw 0 heads from the fair coin plus the probability that we saw 1 head from the fair coin plus probability that we saw 2 heads plus the probability that we saw 3 heads from the fair coin. Okay, so this is just a bunch of Bernoulli problems now. What's the probability that we saw exactly 0 heads? That's 10 choose 0 times the probability of success is 0.5 times 0 times probability of failure, which is again 0.5, tails times 10. Okay, so that's that one. Then we can do the same for 1 head. That means we saw 1 head times probability of success, 0.5 to the 1 times probability of failure, again 0.5, and we saw 9 tails, right? And so we can do this for the rest of them, and let me just go off and do that quickly so that we can get a nice idea of what this number should be. So this is apparently 0.172 chance that this ended up happening. We got less than or equal to 3 heads even though the coin was fair. So it's still possible. It's just not super likely. Okay? So that's the probability that we reached an incorrect conclusion if the coin was fair. And then we have the other side of the coin. Pun intended. So we reached an incorrect conclusion and the coin was biased. Alright, so that means that we said it was fair. We thought it was fair because we saw at least 4 heads, right? We saw at least 4 heads. So what we can do is find the probability that we saw greater than or equal to 4 heads on the biased coin. Okay, so this is going to be like, okay, what's the probability that we saw 4 heads plus the probability that we saw exactly 5 heads. These are all separate ways to do this, right? Plus the probability that we saw 6 heads plus dot dot dot. Probability that we saw 10 heads. Crazy, but possible. And so this is all the same again. It's all these Bernoulli trials, except it's the unfair coin this time. It's the biased one. So what's the probability that we saw 4 heads, for example? That is 10 choose 4 successes, times, okay, what's the probability that we see 4 heads, 0.3 this time, times, or to the 4th power, times 0.7, probability of failure, to the rest. That's 6. And if you do this all out together, the answer that you get back is 0.35. So 35% chance that you end up guessing this way, okay? If you get 4 or more heads from the bias coin, you have a small chance, not the majority of the time, but it's still quite possible to guess wrong when it's the bias coin, which is a bit better than part A, okay? So yeah, these are your chances of making money, okay? That is the gambling problem, and that's our last one for the day. So before we go, I just want to show you one nice example of all this probability stuff with actual computer science topics before we go. So let's talk about hash tables. When we have a hash table, we really don't want any of those keys to conflict. We don't like that, right? We don't want to have multiple keys trying to get at the same bin in the hash table. We don't ever want to double up, because sometimes we have to like make a list, we have to start chaining these things, or we have to find a new slot in the table. It's just a bad time. We don't ever want our hashes to collide, okay? That's the hope. So really, for hashing, we would like to make each bin equally likely for every value. If that's done, then our odds are as small as they can be. But let's see what they are still, okay? What's the probability that you see a collision in a hash table with n slots for keys and m keys to insert? Well, this is the birthday paradox all over again. You just do the opposite. It's easier to find that. So it's 1 minus the probability that you see no collisions at all. And that's the probability that you see at least one collision, right? And so this is 1 minus, well, it's the probability that the first key has no collisions, which is perfectly likely always, assuming the table is of non-zero size. and then that's times the second key has no collisions, times the probability that the third key has no collisions, on and on and on, until we have the probability that the nth key has no collisions. Okay? And so, yeah, all the keys are random in this best case, and each slot is equally likely. So here is our probability. It's 1 minus 1 over, or times n minus 1 over n times n minus 2 over n. This is the probability that the second key has a conflict, has a collision, the third key has a collision, all the way down to the nth key having a collision. And so, for example, if you had 2 to the 32 different possibilities, so you had a 32-bit hash key value, and you were inserting 77,163, your odds are 1 in 2. That's your birthday paradox. You have a ton of space, we're talking billions here, and you only insert 77,000, your odds of a collision somewhere are still 1 in 2. That's our birthday paradox. And this gets a bit more fancy when you have like 64-bit hash values, 160 bits for a key. Please take a while to look at this fun little table. Even when you have almost 1,000 in a very, very large key space, you still have a 1 in 10,000 chance of colliding, okay? And things get a whole lot better when you double the amount of space for your keys, double the amount of size of each key. Because now 77,000 has a, you have to, or it's not 77,000 to find a 1 in 2 odds of a collision when you have 64 bits for each hash key. Now it's, you can put in like 5.06 billion keys into the hash table, and your odds are still only half, okay? So they can hold a lot more before colliding, which is beautiful. And so, yeah, take a look at this table. It's a nice, fun example of all the stuff that we've been learning. And yeah, that in a nutshell is probability theory. All this stuff from the book should hopefully make everything that I've talked about make even more sense. And so yeah, that is your last thing, your last chapter from the book, which means your last homework is about to be released. And I'm going to get to your last lab in just a little bit. So I will see you there.